MIT researchers developed a method that helps a user understand a machine learning model's reasoning and how that reasoning compares to that of a human. In machine learning, understanding why a model makes certain decisions is often just as important as whether those decisions are correct. For instance, a machine learning model might correctly predict that a skin lesion is cancerous, but it would have done so using an unrelated blip on a clinical photo. While tools exist to help experts make sense of a model's reasoning, often these methods only provide insights on one decision at a time, and each must be manually evaluated. Models are commonly trained using millions of data inputs, making it almost impossible for a human to evaluate enough decisions to identify patterns. Now, researchers at MIT and the IBM Research have created a method that enables a user to aggregate, sort, and rank these individual explanations to rapidly analyze a machine learning model's behavior. Their technique, called the shared interest, incorporates quantifiable metrics that compare how well a model's reasoning matches that of a human. Shared interest could help a user easily uncover concerning trends in a model's decision making. For example, perhaps the model often becomes confused by distracting, irrelevant features like background objects in photos. Aggregating these insights could help the user quickly and quantitatively determine whether a model is trustworthy and ready to be deployed in a real-world situation. The researchers used 3 case studies to show how shared interest could be useful to both non-experts and machine learning researchers. In the first case study, they used shared interest to help a dermatologist determine if he should trust a machine learning model designed to help diagnose cancer from photos of skin lesions. Shared interest enabled the dermatologist to quickly see examples of the model's correct and incorrect predictions. Ultimately, the dermatologist decided he could not trust the model because it made too many predictions based on image artifacts rather than actual lesions. In the second case study, they worked with a machine learning researcher to show how shared interest can evaluate a particular saliency method by revealing previously unknown pitfalls in the model. Their technique enabled the researcher to analyze thousands of correct and incorrect decisions in a fraction of the time required by typical manual methods. In the third case study, they used shared interest to dive deeper into a specific image classification example. By manipulating the ground truth area of the image, they were able to conduct a what-if analysis to see which image features were most important for particular predictions. The researchers were impressed by how well shared interest performed in these case studies, but the researcher cautions that the technique is only as good as saliency methods it is based upon. If those techniques contain bias or are inaccurate, then shared interest will inherit those limitations. In the future, the researchers want to apply shared interest to different types of data, particularly tabular data which is used in medical records. They also want to use shared interest to help improve current saliency techniques. The researcher hopes this research inspires more work that seeks to quantify machine learning model behavior in ways that make sense to humans.